Good morning, students. The next lecture is like a small signal analysis of amplifiers. The previous lecture we have discussed the need of biasing, and following that we have discussed a different type of biasing circuits, right? So we'll continue to that. Today we'll see the small signal analysis, that is the AC analysis, and also we are going to see the hybrid pi model for common emitter circuit, and a frequency part. We'll be discussing the whole thing in this today lecture. Okay, so first, when you are doing the small signal analysis, what are the assumptions need to be considered? So you want to assume like a DC source set to 0. That is the thing it is given in the slide. So you want to consider DC source is set to 0. The total response of your amplifier is a sum of your two individual response. That means I can do the individual analysis of AC and DC analysis separately. Okay, so this complete material, this the source of the information which is given in the today class is from the chapter 6, that is a BJT amplifier. So the book I followed Donald A. Neamen, Microelectronics Circuit Analysis and Design. You can use him for referring this same topics. Seeing this given here you can see the diagram. This is your transistor. You consider this your transistor. Here I am providing a DC supply and small signal is your AC input. This signal is giving a small input, that is amplified. Okay, you can see in terms of common emitter, if you see, you have only the phase shift with the magnified output. Okay, so circuit is grounded. So another thing you want to remember, whatever we discussed, everything we have used common emitter amplifier for our reference. Okay, so before we are going to the very important topic, you have to be very clear in the notations. Okay, so here in this small signal analysis, in the you have a DC point, so you have to be very clear. I have fixed the quotient point. You see, I fixed the quotient point. Above that, your signal is superimposed. You can see the positive swing and negative swing. Similarly, this is your input current and output voltage. Here, the important thing you have to remember is here. See, when you are writing when you are using the DC analysis. When you are using the DC analysis, you have to represent with the capital letter. See the capital I in the subscript, you can see capital B. Capital V in the subscript, you can see BE. We are using the AC analysis, that is a instantaneous AC value, signal changing with respect to time. Small I, small b, small v, small b for all parameters. Like all parameter means IC, you can see here IC, your IB, VBE and VC, all parameters. Another thing, if you consider the total instantaneous or total phasor values, see the total instantaneous in the sense it is a combination of AC and the DC. The complete integration part, the total analysis part. So you can see here, so this is your DC point and above your signal is flowing. So if you consider this in the case of ICQ and this is the case of small IC, this complete part is your small I capital C or capital I and small c in terms of phasor. You can represent in any form. So the combination of AC and the small signal values and the DC values is called total instantaneous. It should be represented by small I, capital C. Okay, you have to be very clear in that. Okay, so AC analysis completely have to represent in the small letters, and DC analysis have to represent the capital letter. That what I explained here. Okay, here you can see like you have a source signal and your battery 1 is biased for the base terminal, and IB is the current across your RB resistor, and VB is a drop across your junction 1, and this is your J2, and this is your output port with the voltage drop of VC, and RC is your output resistor. Continue to the last slide. Like I just duplicated this slide. Okay, so you can understand, because this is your circuit, and this is your response of your output graph. Okay, already you discussed it here, so I'll just skip it. So this is like something important, that's why I kept on the slide. Nothing but you can understand here. Here you can see here like a DC part. This is your DC part, right? This is your DC part, and this is your AC part. The DC signal, this is a DC value, this is a time varying signal. That sum is nothing but a total instantaneous part. So these are the variables, important variables for your circuit, that is input current, output voltage, input voltage. That is a sum of your DC value and your AC values. So like what you want to understand is your AC values are superimposed on the DC values. Okay, that gives you a total instantaneous values. See, if you consider your signal source is 0, okay, you might be writing like a VBB equal to IBQ RB plus VBQ. This is your DC equation. So consider I'm adding your small signal in the circuit. So along with the DC, I'm adding a time varying signal. So this IBQ will be a sum of your small IB. So that means I should represent in the small I, capital B. That is the total instantaneous part. So already I have defined what is the small I, capital B. This total instantaneous part, that is a sum of your DC and AC value. Just plug in and you will be getting this final equation. So this is for input base emitter loop. Similarly, I have given for a collector emitter loop also. Okay, so with the continue to the last equation, they rearranged this equation. Okay, these are the rearrange the equation, that's all. Okay, similarly they written for output collector emitter loop, and they are superimposed, and finally they have rearranged the term. Okay, so I think you can go through it. Okay, so no need I think more explanation in this slide, you can understand. So now is a very important, so you can clearly observe here. See, this is a given circuit. I want to convert this given circuit into the AC equivalent part. How? The first thing what you want to do is, I want to consider your DC supply to be 0. I want to remove, actually this is the first assumption I want to do. Second assumption, your DC supply, see, you can remove this part and you can remove this part. Then the corresponding passive elements to be connected to the ground, that's all. See, that's what they have done here. See, I'll draw here for your more understanding. First, always draw the transistor. Okay, so this is your conventional current direction, as I said, as we discussed in the earlier, always coming outside from the base. See, now I have marked the terminal and you encircle. Always you can do it. Okay, now like you have a RB. Okay, you have RB, you can put RB here, and following this you have a source signal. Okay, in the DC, in the AC analysis, okay, you want to consider your small signal VS, and this to be removed, right? So I have removed from the circuit, and I have removed, and this DC also I have removed. Okay, that means you will be getting like this, right? A RC, and it should be connected to the ground. The current across this part is your small I, small c, and defining again, this is small signal part, that's why small I, small v. So the drop across this port is small v, vb, and plus or minus vc, the output voltage drop of the collector terminal. So this is circuit drawn. So the assumption you want to be make clearly, okay, the DC part to be removed and capacitor to be short circuited. Okay, these are the two assumptions you want to be very clear when you are doing the AC equivalent circuit. Now, for before you are going to like a small signal model, the first thing is I want to remove the DC part, then I want to short circuit the capacitor, then third is you are replacing a transistor into the mathematical model. Okay, that is a very important. I want to replace your transistor into the mathematical model. That is a like an internal mathematical expression of your transistor. Like the parameters, so which I use for the like a mathematics here is R pi, GM, and R naught. These are the three important and I can say the powerful parameter I will be using the small signal part. So those part I will explain in the coming slide. So first let me start with the R pi, then we will move to the GM and we will go to the R naught. I will explain you step by step. Okay, the first we will see what is the R pi. That is a very important part. See, I have given you explain detailedly. I'll just read out some very important point. The base current versus base emitter voltage characteristics with the small time varying signal is superimposed at the Q point. That means what they're trying to say is I am drawing the small I, capital B, and small v or VBE. So you want to see them like a performance part of the input side, right? So here you are fixing the quotient point. You are fixing the quotient point like a IBQ, and you will be having your corresponding load line plotted like your DC, your AC superimposed on the DC point. This is your upper swing and this is the lower swing. Okay, see, we can see there is the non-linearity, right? There is a resistance. The changes of IB with respect to the VB. So there is some resistance in between the IB and VB part. That resistance is nothing but your R pi. Here it is plotted for IB versus VB, right? That is a reverse of your V by I. So I can write this slope. This slope is nothing but your 1 by R pi. So there is a change in your IB current with respect to the change in the input voltage. That is a VB or V pi. So I am repeating again. So there is a change in the IB current with respect to the change in the V voltage. You will be getting your R pi. So here it is plotted for IB versus VB. That's why I am taking it's 1 by R pi. So which continue to that, you can see I have given you clearly. I have given step by step. The slope is 1 by R pi because it is plotted for IB versus VB. So the 1 by R pi is nothing but the changes of your IB. The changes of your IB, you can see a changes of IB with respect to the changes of your VB. So that's what it is given you clearly. And we know that the basic current education, I equal to I naught exponential of VB by VT. Okay, that is the basic current education. I was rewritten like a IC in terms of your parameters. I rearranged. Your output current is IC, and IS is your reverse saturation current. It varies from 10 to the power minus 4 to minus 18. The exponential of V, it was customized like a base emitter because we are doing for like a base and emitter part. So that's why it is like a VBE and divided by VT, thermal voltage. You know thermal voltage 0.026. So you know the powerful relation, that is IC equal to beta times of IB. So from this I can write your IB equal to IC by beta. Okay, so I am I'm substituting here, right? So now what you want to find is what is your IB is IS by beta exponential of VB by V of t. How I have explained you the changes of IB by VBT. So I already said the IB equation is IS beta exponential of VB by V of t. Okay, with this relation I have rewritten the IC equation. IC is your IS exponential of VB by VT. So you have a relation IC equal to beta times of IB. So IB is nothing but your this IS divided by beta exponential of VB by V of t. So this is the equation I am getting. Now you know the relation, that is the changes of IB by VBE. So you are doing the differentiation with respect to the VBE. So you will be getting 1 by VT IS by beta exponential of VB by V of t. So this whole term is called IBQ. So IBQ by V of t. So now I want to rewrite in terms of R pi. So I just 1 by R pi I have taken in terms of R pi. I am doing the reverse. So you will get a VT by IBQ, that is a VT, the ratio upon VT by IBQ. So you know the relation of IBQ. The IBQ is nothing but your IC by beta. So if you substitute here, the beta will go to the numerator and beta VT by ICQ. So the final thing is R pi. The R pi is nothing but your beta times of VT by ICQ. So remember this equation, very important to solve your numericals. So R pi is nothing but a beta times of VT by ICQ. So now we'll go for the finding your transconductance. Okay, the transconductance, you know, generally that is a basic definition. The change in the output current, the change in the output current with respect to the input voltage, that is a basic definition of your transconductance. So that is written here. You can see the change in the current with respect to the input voltage, that is a quotient point. In the quotient point your small signal is swinging, right? That is a superimposing part. What is the condition is here is I have a DC point. In the DC point you have a superimposed the DC signal is superimposed, that is a varying signal, and this is your fixed quotient point. So you know the basic relation, like IC equal to IS exponential of VB by V of t. So you want to this is your IC equation to get a your transconductance. So it should be it's a typo error, it should be like a GM. Okay, so this is a GM actually. GM is nothing but a changes of current with respect to VB, and you know the basic relation that you've seen the last slide also. IS is exponential of VB by V of t. If you differentiate with respect to VB, you will be getting your 1 by VT IS exponential of VB by V of t, and that is ICQ by VT. Okay, with continue to that, what is your GM? I am repeating again, the GM is nothing but a ICQ by V of t. That's it. So now you know R pi, you know GM, just plug in R pi is beta times of VT by ICQ, and your GM is ICQ by V of t. If you cancel this both the term, you will be getting beta. So that is product of R pi into GM is nothing but your current gain factor beta. So R pi is your base base diffusion resistance, and GM is your transconductance. R pi is a resistance between the base and emitter, that is a mathematical resistance. That is a resistance of the small signal part. Okay, so the mathematical resistance existing between base and emitter, that is represented by R pi. So the other name is a diffusion resistance. So another relation is very important. So beta IB is equal to GM times of VB. Here in terms of current gain, in terms of current parameter, here in terms of voltage parameter. Current means that is the input current in terms of input voltage, right? So both are equal. Beta IB is equal to GM times of VB. I have explained here. So basically HI is a input resistance that can be written like a VB by IB. That is a basic you have studied in the last course, right? So now you know the HFE IB. Okay, so HFE IB I am taking that product. So IB from this equation I can write the IB is nothing but a VB by HI. I plug in here. So after that I have written this. How you can see here, HFE is nothing but your output current by input current. That is a basic definition for the HFE. HIE is nothing but your VB by IB. Here I have explained. Okay, you substitute here. If you substitute here, if you substitute this part and this part, both IB will get cancelled and you will be getting IC by VBE. Okay, so if you substitute here, what you are getting? GM. So that's what I have written here. If you substitute HFE, that is IC by IB, and HI is VB by IB, both IB will get cancelled and you will be getting your IC times of your VBE. Okay, so the beta IB is equal to GM times of VBE. So this what the understanding. Okay, so this part is your, when this part you are getting GM. So GM is multiplied with the VBE. So now I hope you understand the beta IB is equal to GM times of V pi. So now is a very important part. See, the already explained you like a important parameter, right? So like I said clearly R pi GM, and the product of R pi GM is nothing but a beta. I explained. There is another parameter R naught. So I will explain you that part also. The R naught is your like a output resistance. Okay, so it is like a respect to the yearly voltage. So I am not going in detail. I'll just I'll explain with the characteristics curve. Like if you see the output characteristics curve, you can see IC versus VCE, and you can see your output representation like this, right? Right. See, you can see here after the saturation region, the current is in the active region. It was constant. That means the changes of IC with respect to VC is nothing not happening, right? So it was saturated. So if you see what is the resistance in this part, the output resistance is like it is plotted for IC versus VC, that is 1 by R naught is like infinity, because you have no changes, right? But it's a normal useful case. But if you think there is a change in the IC current with respect to the VC, the moment the current is increasing, right, at that IC, right, that moment we will be taking your VCE as a VA voltage. So what actually happening is the base width modulation. So that you want to understand. Already you studied. So emitter, base, collector. So when you just consider, don't think about the input part and consider about only the reverse part. You are applying the reverse bias here. So NPN, this P is connected with the minus and N is connected with the plus. So if you do the reverse bias, so this you will be having the depletion part. So without the base will be modulated and keep on like in one place the base will be completely disappear. The full part will be occupied by the collector section. Even that I am keep on rising your output voltage. So this junction will break and the current will be starting to rise linearly. But the expected part is your current should be like a constant, but is increasing with the change in the VC. That means your junction is breaking and current is starting to increase linearly. Okay, so that moment is called like a related to the yearly voltage. So that VC is like an equivalent to the VE. Okay, so with respect to that, this equation was written. So this is the output current equation with considering the yearly effect. So you know that what is the IC is nothing but IS exponential of V by V of t, but I include this term, that is 1 plus VC by VE after considering the yearly effect. I am not going to explain you how you getting this equation, that you studied in the previous course, right? So just consider after considering yearly effect you will be getting 1 plus VC by VA. Okay, so like both are not same. VA is the voltage at which the IC is starting to rise. So that voltage is said to be the yearly voltage, right? So now if you I want to find what is the changes of IC by VC. If you differentiate with respect to VCE, VCE, you will be getting a like a 1 by VA IS exponential of VB by V of t. So you will be getting your this complete term is nothing but a ICQ, that what we studied, right? That is a basic equation. The IC is nothing but your IS exponential of VB by V of t. With that it was calculated, and 1 by R naught equal to ICQ by VA. So I'll just I will explain you how to draw the like a mathematical modeling. Very important step. So you can listen to me carefully. So first step, I'll explain you here. This transistor, repeating again, I'm going to change into the mathematical modeling. So first step, see, you can put like same what I am explaining here. Okay, so first put a one center line. Just you can name like a emitter. This is a common terminal. The input terminal I am just naming like a base, and the output terminal I am naming like a collector. So what we learned is, in between the base and emitter you have a mathematical resistance, that is your R pi, right? That is a R pi, that is a diffusion resistance. Okay, the drop across this R pi is nothing but your B pi. Okay, so here you can understand this is a point between the base and emitter, so I can write like a capital V, small v, or small v, or VB. Okay, this is a small signal values, and this is a representation of total instantaneous part. Okay, so you can write anything. So like it is working in the active region. So your transistor is working in the active region because you are doing for amplifier. So you know that in the active region your output current will be a beta times of IB, right? So already I said beta IB and GM VP are same, right? Another thing you want to understand, that BE is nothing but a pi. So I can write VBE is equal to V pi. Base emitter is equivalent to the pi mathematically. So VB is equal to V pi. So in the output in the output current will be a product of GM into VBE. How? So already said IC equal to beta times of IB, and also I can write like your GM is nothing but your output current by input voltage. So I can write your IC is nothing but a GM times of your V pi. So GM V pi is equal to the beta times of IB. I explained. This is in terms of input current, this is in terms of input voltage drop. So in the IC current will be doing your beta times of IB or GM times of V pi. Both are same. This is in respect to the current gain, this is in respect to the input voltage drop. So this is the dependent source, this is a dependent current source. Both are dependent current source. Okay, so this is without considering the early effect. That means in the normal case, I am repeating again. So so you can understand. Okay, so the resistance between base and emitter will be your RP, and this is your the changes of this is a current gain factor. This is a current gain factor, dependent current gain factor. So another thing you want to observe here, you want to do the current notation, that is your capital I small v, capital I small c, and capital I small e. Okay, so this is your basic idea to draw your hybrid model. So first you want to put your emitter terminal, and you want to put a base terminal, and you want to put a collector terminal, and the resistance between this part is your R pi, and the current across this part will be capital I and small b and capital I and small c. This drop is your b pi. Okay, this is with respect to the input port, and also I said the v pi is equal to vbe. Okay, then the output current is nothing but your product of gm into v pi or beta times of ib. I explained right now, right, how this is coming. So in the active region, you know, IC is nothing but a beta times of ib. In terms of voltage, it can return like a gm v pi. Also you can relate with your gm. The gm is nothing but your IC by v pi. So from here I can find your IC current is nothing but a product of gm into v pi. So also related this gm v pi to beta times of ib. Both are same. Okay, so both are equal, that you want to understand. So this input drop is your this is your VB, and this part is your VC. This is without yearly effect. That means I am taking your R0 as a infinity and I am constraining the open circuit in the small signal part. With that, this was made. So here you can see I have drawn your see you have R pi corresponding drop. Already said V pi is equal to VBE, and this is your input current and this is your output current. So this is your input base resistance. RIB is the resistance with respect to the base terminal, and ROC is your output resistance. Here you can see the R0 I have included. The R0 is your resistance because of the change in the IC with respect to the VCE when you are considering the early voltage. If you don't have if R0 is infinity, that will be considered the open circuit. If you are taking your early effect to the consideration, that R0 you will be adding in your model. Otherwise I can remove this R0 by considering R0 as a infinity. That's all. Okay, so with the early effect, the previous model is a without early effect. That's it. Okay, so I can put the hybrid pi model just to have idea. Okay, so first what we want to do is, first you you want to change into the AC equivalent circuit. So what you want to do is, we want to remove this DC supply, right? We want to remove the DC supply from here, and the capacitor should be short circuited. Okay, so first let me draw the transistor. So I given another circuit also in the next slide. You can try yourself. Okay, so emitter base collector. So this capacitor is going to be short circuited, and following you have RS resistance, and here you have a input voltage Vs grounded. Now if I remove this VCC, this R1 will come to the ground, right? The passive elements will come to the ground. So that means it will come parallel. So R2 and R1 will become parallel, right? I am repeating again, I am removing this VCC so that R1 will come to this, connected to this ground. So here I can see in RC this also removed, so this RC also will connected to the ground. So here you are taking your output point, that's all. What is the next step? I want to replace this transistor to the mathematical modeling. How you will replace? The first step, put the emitter, then you have a base. So mark the current terminals. Okay, so in between base and emitter you have a resistance, mathematical resistance R pi. This is a resistance between the base and emitter that drop across this V pi. So the output current, you can write it as a beta IB or GM times of V pi. So always I forgot to say in the in the modeling, the current IC is looking towards the emitter current because this is the conventional current direction. So you can see here the collector current is always looking towards the emitter point. The collector current is looking towards the emitter point. So you have to be very clear, the current from the collector, it always look towards the base terminal, look towards your emitter terminal, you can see. So that's why the arrow was going down based on the configuration. Suppose if I am doing for common collector configuration, so the collector will come down, emitter will go down, up, right? So that time the arrow will top. The ultimate thing is the collector current it look towards the emitter terminal, that's all. So the collector is top and emitter is bottom here. So in this case the collector current is looking downward. If emitter is coming top in the other configuration, you want to change this direction towards upward direction. So this is equivalent for this transistor, right? Here I have not considered the L effect. If you want, you can add or not, that's all. So the small signal part is completed. Now we want to add this external resistance. The mathematical part is completed. So add this resistor part, R1 parallel to R2. I have added the single resistance, that is R1 parallel to R2. Following that, you have a source resistance RSI, that is a signal, this source resistance RSI. Then this RC. See, these are the external elements. These are the external elements. This is a mathematical part. Up to this mathematical part. So these are the external element and these are the internal mathematical part. I hope you understand, right? So I'm given another one, so you can try. Okay, you can try, and if you need out, we can discuss. The thing only is I have added RE down. In the previous circuit, the RE is not there. This is without RE resistor. Here I added the feedback, so I'll just give the hint, you can try. So here you have an emitter and here you have a base, here you have a collector. So like so here the current will be IB and here the current source will be IC, and so here you take it as an emitter, and below emitter you have like in the RE, in the emitter terminal you have RE, right? So that it's connected to the emitter terminal, and current across this will be your IE. So that is away from the terminal. This both coming towards. So the IE is nothing but your IB plus IC. The remaining part I hope you can try. Okay. So and add your external elements. With that you will get your complete model. Okay, so this is already I explained you, that is a beta, it is again it is given here. So another thing very important to proceed to the for a common emitter derivation part, that is your this complete part is your like a RIB. You want to understand what is a RIB. RIB is a resistance when you look into the base terminal. So that is nothing but your V in by IB. V in by IB. Okay, so that I will explain you. So V in something here. Okay, so here. Okay, so here is your V in. So V in by IB is your nothing but your RIB. Okay, that is your base resistance RIB. The coming slides I will explain you. Now you just get an idea how this V0 is written. V0 is a VCE, you know. So you understand how this equation is coming, very important. So V not equal to I into R. So there is a basic Ohm's law. So in our case the output current is IC. And always you remember the IC current and IL current both will be opposite. So consider your load current will be something opposite. So IL plus IC equal to 0. So always the load current and conventional current direction IC will be opposite. With this assumption, this minus I will be adding in your equation. This minus only saying that there is a phase shift between the input and output signal. So that IC. So what is IC actually you have calculated, that is GM times of Vp. Okay, so if you write what is the final equation you will get for V naught, so that is minus Gm V pi into your RC. So with that this equation is coming. Then when you see what is a V pi, what is a V pi, if you want to calculate V pi, so you want to apply the voltage divider rule, that is a source voltage, the voltage divider rule, you know, you are familiar, the corresponding resistance divided by sum of your total resistance, so R pi plus this is your RB, so that gives your V pi. Okay, so when you want to find a gain, the basic formula is output voltage by input voltage, okay, the output voltage is V naught and input voltage is Vs. Okay, so I want to find a voltage gain, so very simple, you substitute this V pi here. Okay, so if you substitute, you have a Vs in this V pi. Okay, so that V naught will become minus Gm R pi divided by R pi plus RB into Vs RC. Now I want to calculate V naught by Vs. So if you divide this V naught by Vs, you have V naught after substituting the V divided with the Vs. So from this V pi Vs will cancel. So the final voltage gain will be minus Gm RC into R pi divided by R pi plus RB. So this only for your understanding how your AC and DC are superimposing your source voltage and your current. This is your source voltage and base current. This is your output current. This is output voltage. So you can see here input and output have a phase shift of 180 degree. That's why in common emitter, in the BJT, in the common emitter, the minus will be coming in a voltage gain. Similarly, in the MOSFET, in the common source, minus will be there. That minus saying there is a phase shift between your input and output signal. Okay, so I just given one problem relevant to the lecture, like a small signal part, very basic problem. So you can try. Okay, so like the given parameters are beta equal to 100 and VCC is 12 and VB is 0.7 and RC is 6 kilo ohm and RB is 50 kilo ohm and VB is 1.2. First step, I am repeating again, the first step is first you want to find a DC analysis, then you want to proceed the AC analysis, then you want to find your voltage gain and your resistance part. The DC biasing parameters are ICQ and VCQ and IBQ. AC parameters are R pi, GM and R naught, and you want to find output resistance, input resistance and your following your gain. Okay, so here I have given the value, like already you discussed the DC biasing. From that this formula is written by applying the KVL in the input circuit and output circuit. You got these values, IB equal to VBB minus VB on by R by, and IC equal to beta times of IB and VC equal to VC minus ICRC. So if you substitute the given values, all values are given, so all values are known for you. Just you want to plug in from here to here. So from here to here you just plug in. So if you plug in here, you will be getting your output, your DC parameters, that is your 1 milliamps and 6 voltage. You can try. Okay, so take the calculator and try. So the R pi is beta VT divided by ICQ, that's what you studied. So beta is 100 and VT is thermal voltage 0.026 divided by 1 milliamps, so that you will be getting 2.6 kilo ohms. Similarly for GM, just plug in the values, you will be getting this 38.5. So you know the formula for voltage gain, you have studied, right? It is GMRC into R pi divided by R pi plus RB. So just plug in the GMRC known values, you will be getting 11.4. So that what is the observation is the magnitude of signal output voltage is 11.4 times of sinusoidal input voltage. So that it is magnified. The magnitude was increased. How much time? The 11.4 time was increased. That is your observation from this problem. Okay, so when you see calculating the input and output resistance is very important. when you want to find the input resistance, like you want to see from the left side. Okay, consider we are looking from the left side. So I am repeating again, RIB means that is a base, that is a resistance in the input side. It's looking towards the base. So when you look into the base, you can see the only the resistance is R pi. So like a input resistance is looking into the base terminal of the transistor, that is RIB is R pi, it was given here. Okay, so similarly when you find for when you want to find for output resistance, the ultimate thing is you want to short circuit the input low. Okay, you short circuit the input, then your V pi will become 0. So this is also is 0. So GMVP also is going to be a 0. If it is a 0, your output resistance will be only the R0. So I'm short circuit the input element. So your VB, that is equal to V pi. So V pi is equal to 0. So that GMVP will be 0. So that your output resistance will be R0. That is